All right. Welcome to the DDPS seminar, everyone. Before we introduce our invited speaker, let's go over some rules and logistics. First of all, please mute yourself during the talk unless you have questions. If you have questions, you are welcome to unmute and ask. Otherwise, please use chat room to post your questions so that we can address them in Q&A session at the end. Second, today's DDPS seminar is open to external audiences. Therefore, no classified discussion is allowed, so please watch out. Finally, the talk today will be recorded and uploaded in our YouTube channel. That's about it. Now, let me introduce our speaker today. It is an honor to host Lexing Ying, who is a professor of the mathematics at Stanford University, where he is also a member of the Institute for Computational and Mathematical Engineering. He specializes in scientific computing and numerical analysis. In particular, his research concerns the design of numerical algorithms for problems in scientific computing. Ying received his bachelor's degree in computer science and applied mathematics from Shanghai Jiaotong University in 1998. He received his PhD from the Courant Institute at New York University in 2004. Under the guidance of Dennis Jorin. Before joining Stanford in 2012, he was a postdoc at Caltech and a professor at UT Austin. The awards Lexing has received include a Sloan Fellowship in 2007, NSF Career Awards in 2009, the James Wilkins Prize in Numerical Analysis and Scientific Computing in 2013, for his outstanding contributions in many areas, including the rapid evaluation of oscillatory integral transforms, high-frequency wave propagation, and the computation of electron structure in metallic systems, and a Silver Morningside Medal in 2016. Today, Lexing will give a talk about Pronys method, analytic continuation, and quantum signal processing. Please expect a wonderful talk and enjoy it. Now, without further ado, let me pass the baton to Lexing by asking our usual question, that is, what is your favorite things to do other than research?
Sleeping.
Oh, wonderful. I like that. That's one of my favorite things to do.
Yep.
Yeah,
Okay.
as well. Okay, the stage is yours.
All right, okay. Prony's method. So, okay, first, thank you very much for the invitation, and it's an honor to give this talk here. And I realized that the seminar series about machine learning, right? So, in fact, so this talk would not be too much about machine learning, but it's more about traditional kind of like applied math and also quantum computing. Okay.
It's not only about machine learning. It's not only. It's a data driven.
Okay, data driven. I see.
Yeah.
Okay.
Yeah.
Good. Then it is data driven then. Okay, great. So so here's the let me see, how do I move? Okay, great. So here's the content of the talk. So the main player of this this talk is Prony's method. So I will spend the first part of the talk explaining what is Prony's method. Then I'm going to talk about some of my recent work on applying Prony's method to do noisy analytic continuation and also do quantum signal processing. Okay. So first, let's talk about what is the Prony's method. Well, the Prony method is the way it's usually presented is trying to solve a problem like that. So suppose you have a function fx. It's a linear combination of a few Fourier modes. So here, d is the number of Fourier modes, omega j is the frequency of the Fourier modes, and rj is the weight of the Fourier modes. Okay, and you can observe fk's at uniform samples, uniformly sampled location. So here we just assume that fk is observed. You're given fk at the integer values of k. Okay, it doesn't need to be integers, but integer make things easier. So then the question is that how many frequencies do you have in the signal? Can you discover that? And then can you figure out what is wj's, which is the frequencies, and also what is rj, the weights? Okay. So classical solution, which go back more than 200 years, is called Prony's method. And this method itself is well known, I believe, in the control community and then also in the EE community, double E community. But somehow through the years, it's got, I wouldn't say lost, but it's got buried under many other things. I mean, it's not as well known as it should be in the applied math community and the computational math community. So that's why I think that but it's a beautiful method and a lot of application. That's why I want to share with you. Okay. So in the pruning methods, okay, let's take a look. The data we have is fk at integer values of k. So let's denote it by f sub k. So this can be written as a linear combination of these Fourier modes evaluated at the location k. Now, the goal again, recall that we want to figure out what the d is, what the wj is, what rj is. Now, what we're going to do first is we're going to consider the Fourier modes one by one, okay? So let's consider Fourier modes at the frequency wj and at all the integer values. And this will give me this column vector here. So this is the first vector on the left-hand side. It's an infinite long vector. Now, what we're going to do is that we're going to consider this upward shift operator S. So essentially shift everything by one slot upward. So it's an infinite long vector, so you shift it, it's still infinite long vector. So once you shift it, that the case entry will be e to the I omega j of k plus 1. Now, because of the nice property of the exponential function, this is equal to e to the I omega j k times e to the I omega j. So therefore, if you reshuffle the things a little bit, you get this formula s minus e to the I omega j times my infinite long vector is equal to 0. Now, this is what happens with one Fourier modes. So I have this s minus e omega j operator. But let's just take the product over all the Fourier modes and consider this product operator applied to the same infinite long vector. Because there's only one operator s involved, everything commutes. So therefore, this product applied to this vector is still 0. Now let's do a linear combination on this j now. So each of the column itself have until one Fourier modes wj, but now, but the j is arbitrary. So therefore, I can just multiply each of them by rj and then take a sum. So because the equation here equal to 0 equation here is linear, so therefore, if you take a look at this thing, it's still 0, right? Now, but what do we have is in this new infinite long vector? If you go back to the first line, it's in fact every entry is just fk. So therefore, what this means is that if I take the product of these shifted operators applied to this fk vector, it's equal to 0. Now, why is this useful? The reason why it is useful here now is that because now you can see you have the product of operator appear here. So therefore, I can write this as a polynomial applied to the operator s. And so this polynomial obviously take this form. It's s minus e to the I omega s. Take the product. This is equal to mz, and this is equal to m0, blah, 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 blah. So recall that we don't know d here because we don't know how many terms we have in our Fourier, our signal, and we don't know these coefficients. And this is in fact something we want to discover. Now, if you plug s back into this product of operators and take a look at the previous formula, this operator now becomes m applied to s. So you have m applied to s is equal to, apply this to this vector fk is equal to 0. But what is m applied to s? It's just corresponding to apply s multiple times to each of this vector, to this vector f, right? This f is corresponding to this long vector. So therefore, I get this formula. So I have different shifted copies of f and multiply with certain constants m's is equal to 0. And then you write this in the matrix form. So this is my vector f. The first vector is my vector f. Okay. And then the second vector is my shifted sf, and the next vector, so on and so forth. The last vector is sdf. And these vectors do a linear combination with weights m0 to md is actually equal to 0. Okay. Now, what does this tell us? This tells us that, in fact, the rank of this matrix has to be d. Right? Because what I showed you here is that by putting d plus 1 vectors, you're going to find the coefficient m0 to md is equal to 0. But however, because I have exactly d Fourier modes, any matrix with less than d plus 1 columns will be full rank. So therefore, by taking a look at this matrix, you'll be able to figure out what is the rank, and the rank is exactly d, which corresponds to how many Fourier modes in your original signal. And then, by taking a look at null space of this equation here, you'll be able to figure out what is m0 to md up to a uniform scaling constant. Okay? The constant itself doesn't matter, because why? Because what we really care about are the roots of this polynomial mz. So therefore, if you find the roots of this polynomial mz, this will give you the frequencies e to the I omega j. Now, here we're almost done, because we know what the d is, we know what the e omega j is through root finding. So therefore, all we need to do is just to find the root, find the least square problem to figure out what are the residuals or what are the weights rj, and we'll be done. Okay? So this is the whole idea of the Prony methods. What you want to do is that you want to form this so-called Hankel kind of matrix and use the rank of the Hankel matrix to figure out d, which how many modes you have, and use a null space to figure out what are the coefficients of the polynomial with the roots equal to this Fourier modes. And then by finding the roots, you'll be able to discover the modes, and by solving least square problems, you'll be able to find the weights. So the Prony method, as I said, is a well-known tool in control and in electrical engineering, but somehow it's not so well known in applied math. It should be. I mean, in fact, it started from applied math, but so yeah. But it's a little bit unfortunate. But I think it's really a beautiful method. Now it's adaptive. It's very good because it doesn't really care about where WJs are, right? And it does not need to require WJs to stay on a certain uniform grid or a pre-specified grid. The location of the WJ just pop out from the root finding process. So it's adaptive. And it's also a direct algorithm because finding the rank and finding the null space are pretty routine numerical calculation. Now you can just open MATLAB or open Python, you will be able to do this quickly. But on the other hand, it also has some shortcomings. So for example, it requires a root finding, which is sometimes a little bit ill-conditioned process, okay? So therefore, that's actually the main disadvantage of the Pronys method, because when all these coefficients f has noise and finding the roots become a slightly unstable process. Okay, so this is the first part of the talk. I share with you what is Pronys method, and I hope it's clear. If not, and feel free to ask me questions before I move on to the next step. Okay, so now I'm going to talk about two applications. Let's start with the first one. It's called a noisy analytic continuation. So analytic continuation in the following problems. Suppose you have a function GC, which is an analytic function on the complex plane, and the function might have some poles, might have some singularities, and you know the function are a set of points, and this set of points could be a curve, could be a line, or could be just a set of discrete points with a limiting point. And what you want to do is that you want to find the value of this function at other places on the complex plane. Okay. So let's first consider simple problems where this GZ is represented by a bunch of poles at CJs with residual RJ. Okay, so this is my GZ. Now, the main difficulty that we face as in practical problems as engineers or scientists is that often you only have noisy access to GZ. You don't have precise values of GZ, and the GZ come with some Gaussian noise or with some other noise. And in this example, I'm specifically interested in the case where the data, the GZ, is given. You're allowed to sample GZ on this purple line, which is the imaginary axis. So this case is particularly important in many quantum chemistry and quantum physics calculations in condensed matter physics. And this is corresponding to the analytic continuation from the Matsubara-Green's function to the so-called retarded Green function. Okay. All right, so the goal here, but mathematically, here's the question. I have access to the GZ value, noisy access to the GZ value on the purple line. What I want to do is to find how many number of poles do I have, what are the location of the poles, and what are the residual of the poles. Now here, I want to make one assumption, which is numerically it's necessary. What I assume that is that my poles, which marked in this picture as a red and also blue here. So let me remark, the poles could be not restricted to real axis, so maybe this picture is a little bit misleading, but the poles could actually move everywhere. These red crosses and the blue crosses could move other places on the complex plane. So the assumption I want to make is that all these poles are included in these two circles, where the first circle is centered at b plus a over 2 with radius b minus a over 2. So essentially, this circle intersects the real axis at 2 points a and b. And the circle on the left-hand side intersects the real axis at the points minus b and minus a. Okay, these are the two circles which include all the poles. So why do I want to make this assumption? The reason that if I don't make this assumption, then it's the problem numerically and algorithmically is going to be hard, because now you can imagine there's a pole which lives very, very close to infinity, right? Somewhere close to infinity. Because of the decay of these, this pole function, and near the origin, you probably don't feel anything, right? So therefore, unless you search along the whole real axis, imaginary axis, otherwise there's no way for you to figure out where the pole locations are. So therefore, that's why we need to make some assumptions about a priori information about the region of the poles. Okay, so why this problem itself is related to the Pronys method? Well, I mean, if you think about the Prony methods I presented at the beginning of the talk, the data is given in spatial and a temporal domain, right? You have the data at a uniform grid X, and then in the X variable, and the basis function, or the things that you want to recover is actually in the Fourier domain. You want to recover the frequencies, right? And how many frequencies are there? But in analytic continuation, the problem is slightly different, is that the data is given in the spatial domain. By spatial, I mean the complex plane. And the thing that you want to recover, the basis function, is also in the spatial domain, because these are the pole location in the spatial domain. So therefore, the problem AC, analytic continuation, and Prony methods, the problem I mentioned earlier is different. but they're related, as I'll show you. So before I dive into the method that I want to present, is that I want to say that this work is actually the problem of analytic continuation has a long history. It's related to the problem of rational function approximation. It relates to Padilla approximation, and then relate to the work, for example, by Berkey and Manzo on approximation with exponential sums. So all these are very important early work. Most of them are set in a slightly different setting, but the thing I'm going to present is actually to borrow ideas from these methods. So I like to say that this is a huge field and a lot of references. So what I have here is clearly a incomplete list, and if anyone has worked on that and I didn't list your reference here, I apologize. Okay, so in order to apply the Pronys method, so the first thing we're going to do is something very simple, conformal mapping, which you probably learned in the first few weeks of a complex analysis class. So recall that our geometry is the following. On the left-hand side, we have this so-called z-plane, which is z is a complex variable we call z-plane, where the purple lines correspond to the place where I can sample my g function, and the two circles are corresponding to where I can place my poles. So what I'm going to do is I do a Mobius transformation, which is given here. I'm going to transfer into the t complex variable. So on the right-hand side, it's a t picture. So what does this transformation do? The transformation is going to send this purple vertical imaginary axis into a unit circle on the right-hand side. And it's going to send the right circle on the left picture, the right to a small circle on the right-hand side, and the left circle on the left-hand side to the big circle on the right-hand side. So essentially, you can think about the geometry has been warped. The right circle shrinked, the purple line become a unit circle, and the left circle got unfolded and to become the bigger circle. Now, but the beauty of this complex analysis is that if you have a pole representative function, which can be represented the pole representation on the left-hand side, after you do this conformal transformation, the warping, it still remains to be a sum of a bunch of poles, modulus a constant. So this is what I'm stating here. If you take a look at the function gt, it can also be written as a bunch of poles at different locations, obviously, because you map into a different space, and also with different weights, different residuals, which I denote by wj here, and plus a constant. The reason is that the pole is the location where the function values goes to infinity. So, I mean, if you can identify where the function go to infinity on the right-hand side, you can also identify where the function go to infinity on the left-hand side. Now, so how do we figure out the poles in the warped domain, the t-space? Well, the idea is to consider the integral of this form. I'm going to let gamma to be the boundary of okay, sorry, I have some mistake here I need to correct, but let's gamma is to be the boundary of the unit circle. So what I'm going to do is I'm consider the integral of this form. It's 1 over 2 pi I integral over gamma, the boundary, of gt over t to the power k dt over t. So the way I want to write this way is because you will see in a second, because related to Fourier transform. What I claim is that the integral of this for different values of k will actually give me information about the poles inside and outside the unit disk. So first, let's consider the k which is less than or equal to 1. So when k is less than or equal to 1, I can calculate this integral. And after doing a few simple steps of a complex analysis, you see that this is actually equal to the sum of all the poles inside the unit circle. This is sum over tau j is about less than 1, and multiplied by wj tau j to the power minus k plus 1. So this is very simple first year complex analysis calculation. So I will not try to repeat here. So what this tells you is that if I take different values, negative values of k, this will actually give me information about different so-called moments of the poles inside the domain. And similarly, if I take the k to be greater or equal to 1, take a look at the same formula, this will actually give me the sum of the poles with a different sign, but the sum of the poles which is greater or equal to 1, which is the negative moments of the poles outside the region. Okay, so this is very nice. And what makes things a little bit more easier is that if you take a look at the integral that I care about, in fact, this is the integral over the unit circle. So when you integrate a function over the unit circle, obviously it's restricted, it's very connected to the Fourier transform or the restriction of the function to the unit circle. So in fact, after doing like some calculation, it's clear that this quantity that I've written down at the beginning here is nothing but the case Fourier transform, the case Fourier coefficients of the periodic function g defined on the unit circle. Okay. Now we're ready to use the Pronys method. How do we use that? Well, Previously, in the Pronys method, I considered a function with vector was infinite long vector in both ends, right? Because I have all the Fourier, all the x's. But here, I'm only going to consider a semi-infinite vector. So let's consider k less than or equal to 1. So we know that they contain information about the poles inside the disk. So let's do that. So let's define the g minus hat vector, which is the negative part of the Fourier transform. Well, negative part doesn't mean that in terms of the value, but in terms of these index, right? That's from -1 all the way to -infinity. And this, in fact, is given by this formula. And in fact, this is given through this calculation that I had on previous slides, because this is equal to this, and this is equal to that. So therefore, this is in fact equal to the minus the sum of all the poles of wj tau j0, tau j1, so on and so forth. Now you see that this is very similar to the formula that the formula that I had in the Pronys method. And now I can play the same trick. I can introduce this shift operator s and minus tau j, and apply equal to this tau j0, tau j1 vector, and this is equal to 0. Because if I shift the one slot, and the vector is multiplied by tau j, right? And I can take the product over all the possible poles inside the region. For all tau I less than 1, I can form the product of these shift operators and apply to my just tau j vector, and that's give you 0, because all these operators commute. Now, again, here I have tau j, but you see that this operator becomes the same. It's independent of j, right? When I take the product, it's independent of the j. Previously, it was dependent on j, but when I take the product, it's independent of j. So therefore, now I can do the summation over all the j's. If I do the summation over the j multiplied by the wj, I recover this g at the j vector. Okay, here, this step is just, last step is just doing linear combination. And finally, and this is equal to 0. Now, you see that we have this product of operator. And by defining the product to be a polynomial, m0, t0, m1, t1, so on and so forth, mdtd, okay? And then write this polynomial, replace t with s, and plug back into this formula. What we get is that m0 times this vector g minus plus m1 times the shifted copy of g minus, and md to sd g minus is equal to 0. Now I can write down exactly what is shifted copy of g minus vector, and write this as a matrix equation, linear system for the MDs. So M coefficients. And this will give me this Hankel matrix, which consists of the negative coefficients of my Fourier transform. Now we can repeat the last step of the Pronys method. But take a look at this matrix, figure out the rank. I will get how many, what D is, and D is corresponding to how many poles you have inside the unit disk. If I look at the null space of this M, vector, null space of this matrix, you'll be able to figure out this M vector, which are the coefficients of the matrix polynomial. And by finding the root of mz, recall that M is defined this way. By finding the root of mz, you'll be able to figure out tau j, which are corresponding to the poles inside the disk. So therefore, by now, I'll be able to figure out what are the blue poles inside the disk. Okay, now you can repeat the same process. For the sake of time, I will not go into the details. Now, but instead that you consider the real part, the positive part of my Fourier coefficients, and they will actually, in fact, give me information about the 1 over tau I, where the tau I are the poles outside the unit disk. So all we need to do now is, again, repeat the same steps, find the m's, find the roots. The roots will be 1 over tau I. By taking the reciprocal of this, I'll be able to figure out what are the tau I outside the unit disk. So by doing these two, going through the algorithm of these two slides, I'll be able to figure out exactly what are the location of the blue poles and what are the location of the red poles on the right picture, okay, in the T-plane. Now, then the next step, once I figure out what are the location of these tau i's in the T-plane, what can I do is that I can combine them together, right? Inside, outside, I group them together. And I use a Mobius transform to bring them back into the Z space. So, sorry for going back to the Z space. Once I go back to Z space, I know where the poles are in the Z space. And then at the last step, I can use the least square to figure out what the residual RJs are. Okay, so that's the whole algorithm. So there's also a matrix version of this algorithm where you can allow this G to be a matrix, and you allow this R to be a matrix as well. So this is also appear quite often in the so-called quantum embedding calculations in quantum chemistry, and this actually, in fact, make the problem a bit easier. So let me show you with some numerical results. So for the complex poles, so here what I mean is that the pole location could be anywhere in the complex plane as long as you stay inside these two disks. So the two disks here are corresponding to the disk with going from A is equal to 1, B is equal to 100. So it's corresponding to roughly about the disk at plus 50 and also another disk at minus 50. To be precise, it's 49.5. So, so here I give 4 pictures, each of them with different noise level. So because we're giving noisy data. First picture, no noise. Second picture, 10 to minus 6, 10 to minus 5, and 10 to minus 4. So noise go up every time multiplied by a factor of 10. So you see that in the first 2 pictures, I mean, we almost recover everything precisely. So here the red circles correspond to the exact location of the pulse, and the blue star corresponding to the recovered location of the pulse by our algorithm, and the green crosses corresponding to where do I sample on the imaginary axis. So, so recall that where do we need to sample? In fact, I didn't mention this, but you see that we need to compute these Fourier transforms. So because in order to compute the Fourier transform, I need to know the function value on the unit circle. I can use trapezoid rule to put the points uniform on the unit circle. And when you do Mobius transform to map them back, and these corresponding to this extended grid, like a stretching grid, gets sparser and sparser kind of grid on the imaginary axis. Now you see that for the first 3 pictures, we recover quite well. But when the noise is really high, the problem itself is a yield pulse problem. So when the noise is large, I mean, you will fail. So this is show you that when the noise is high, in fact, we will not be able to recover the pole which is the furthest away. In fact, the other 2 poles nearby is actually going to be pulled a little bit towards them. So therefore, this is what happened to the high noise regime. And I think any methods would suffer something like that. Okay, so here's a case where we know a priori the poles are actually on the real axis. So in this case, we can actually, in fact, improve the algorithm a little bit by adding this prior information that everything is on the real axis. So here I try higher noise. Previous day is from 10 to minus 6 to 10 to minus 4. Here 10 to minus 5 to 10 to minus 3, 10 times bigger. So again, you see that in the first 3 pictures, we have almost perfect reconstruction, but for the largest noise and it deteriorate. Okay. Finally, this is the case with the matrix value case. And as I promised you, I mean, it's more robust. So in fact, we can jack up the noise. So the noise here is that going from 10 to minus 4, 10 to minus 3, all the way to 10 to minus 2. Okay, this is really large noise. So you see that in the first 3 pictures, no noise, all the way to 10 to minus 3, we have almost perfect reconstruction of the pole locations. And the last one, unfortunately, because the noise is too high, and we missed a bit. Okay, so this is the first example. So in fact, we can actually consider analytic continuation in a slightly harder case. So this is the case that if you open a condensed matter or many body physics textbook, this is, for example, the formula that you will see. This tells you the so-called Green's function over the whole complex plane is in how is this related to something called a spectral function. So in the previous case, we actually considered this case where the spectral function is coming from a bunch of deltas. That's the easy case. And in fact, we allow ourselves to sample anywhere on this Matsubara line, the imaginary real axis. But however, in real scenarios, so you only have noisy excess of the Green's function, not everywhere on the Matsubara line, but only on a very small Matsubara grid. So here, the Matsubara grid is defined to be a uniform grid on the imaginary axis, but this n here typically is only in order of 100 or 200, so it's pretty small. And yet you want to figure out what is the spectral function. So this is much harder to the case I just gave to you, where you allow yourself to sample anywhere on the Matsubara line. So we consider 2 cases. One case is called the molecule cases, and second is called the condensed matter physics cases. So the molecule case is actually similar to what I described earlier, but the main difficulty is that I only have the blue segment, which is a short segment where I mean, in fact, I only have a very small uniform grid. I know the Matsubara, the Green's function data. And but previously, I allow myself to sample anywhere else. In the condensed matter case, the situation is even more difficult because your AX, your spectral function, could be anywhere on the real axis. So therefore, that's a much harder problem. Let me not go into the detail, but just give you an idea about how do we solve these problems. Again, the tool we use is conformal mapping plus Prony's method. So in the first case, the blue line corresponding to where I have the Matsubara data. The red corresponding to where the support of the spectral function. And the analytic function essentially does is that it essentially does a rotation and does an unzipping. Essentially, it's going to send this blue segment into a unit circle by tearing up the complex plane. Okay, so you can think about I'm using a scissor in the middle picture. I'm using a scissor to cut along the blue line and then unzip it to become a circle. And once you unzip it, become a circle, and you can again use the Fourier transform and to apply the Pronys methods. And the last slide shows you the results we have. You see that the noise level go from 10 to minus 6, 4, 3, all the way to 2. In fact, in the case of 10 to minus 4 and 10 to minus 3, we're able to do almost like exact recovery. Very nice. So both in terms of the magnitude and also in terms of the location of the pole. And in terms of the noise level, 10 to minus 2, the noise is too high, so we're a bit off in terms of the location and the magnitude. So in the condensed matter case, which is even more difficult, and the Matsubara, the blue line again tells you that where the uniform Matsubara grid live, and the red line corresponding to the support of the spectral function. We're also going to do a conformal mapping. First, we're going to do a Mobius transform to transform the red line into a circle and the blue line again to a segment. And then we use the same function to unzip the blue segment, use a scissor, cut the blue segment, and unzip it to a circle. Now you see that because it's a conformal mapping, the red circle itself used, and there's a nice red circle in the middle, is going to become kind of like a peanut shape because of the electrical transformation. All right, so the last line tells you what the results are. So in this case, we have 5 spikes. So this, the red corresponding to the true spectral density. So we show different noise level, 10 to minus 7, 10 to minus 6, and 10 to minus 5. You see that in the first case, we get almost perfect reconstruction, and both in terms of the location and also the magnitude. In the second case, the locations are all correct. The magnitude is correct for the 3 middle ones, but the 2 ones at the end points go down. And this is because that when you get further away from the Matsubara grid, the reconstruction becomes less and less stable. And in fact, on the Matsubara grid, you don't feel a lot of information for the poles which far away. Sorry, for the spectrals far away. And finally, when the noise level is quite high, and you see that it will only be able to recover the middle one correctly, and because of the ill-post problem, so there's nothing we can do here because if the noise is too high. All right, so this is the second part of the talk, and I told you how to use the pruning method to do analytic continuation. And now, any questions? All right, so the last part is about quantum signal processing. Okay, so quantum computing is a very hot topic these days, and in fact, I will not be able to, go into the details. But here we only care about one interesting question, is something called quantum signal processing. So let me just explain where the problem come up. So the first is that in quantum computing, all the operators that you're trying to represent are represented, that you can represent it actually in terms of these quantum circuits. So in the quantum circuits apply uniform transformation on a Hilbert space. So therefore, all the operators are actually unitary operators. But however, you're building quantum computer not just to simulate quantum mechanics, right? You wanted to do many other things. For example, you want to do optimization, you want to do solve linear systems, you want to do various other things. So therefore, often, this is also true even in the quantum computing sense, quantum simulation sense, is that you're given a Hermitian operator A, where we can scale it down so the norm is less than 1, and it's n by n Hermitian operator. Now, in order to efficiently represent it on a quantum circuit, the question to ask yourself, is it possible for you to represent A using the only log number of qubits? Okay. Now, this is a hard question. So in general, the answer is no, because if A is not a unitary operator, you cannot represent it by exactly log number of qubits. But the beautiful idea is called a block encoding. It says that I cannot represent A on exactly this number of qubits, but I might be able to increase it 1 or 2 or maybe 3 extra qubits such that I can represent A somehow with this slightly larger this quantum circuit. In terms of the matrix operator notation, what essentially this is doing is saying that I'm not trying to represent A itself, but I'm trying to represent A as the top left corner of a bigger matrix, where the big matrix itself is unitary. So in the quantum circuit, I'm going to represent UA, and if I restrict myself to a small part of the circuit and output, then I will get A. So this is the beautiful idea of quantum block encoding. Now, there's a lot of literature about how to actually give me an A, how do I form this block encoding. So this is a lot of research on that, and this is another topic that I want to get into. What I want to get into is an extra step, is that suppose you give me the block encoding of A. Can I get the block encoding of a function applied to A? Why do I care about that? Because this is really, most of the scientific computing is about. So scientific computing, in some sense, is all about give me a matrix, and I try to do something to this matrix, represent an operator that's associated with this matrix. So for example, suppose let's take a look at this function. Fx is equal to e to the i tau x minus I tau x. This is the problem of quantum simulation, because if A is a Homotonian, this operator tells me the Schrodinger operator, which maps from initial time to a final time, okay, with a time period equal to tau. Filtering is a very important part of signal processing, but filtering is really saying that I'm gonna, on the spectrum, I'm just gonna care about the eigenvectors in a small window, and so this is called filtering. And also, this operator's 1 of x is really just doing inversion, because A inverting the A operator, that's solving linear system, and doing signal processing is all about this inversion. And finally, there's this operator which is called Fermat-Dirac operator. This is like a step function. You care about the spectrum below a certain point, but you want to throw away the rest. Now, so the question is that suppose I have a block encoding of A. How can I get a block encoding of FA? Well, this is answered by this paper, which is called quantum singular value transformation. So what is this work? It's initiated from the paper by Low and Chow in 2017, and also there's this Gillian et al. Paper essentially expanded and expanded a lot of stuff. So what essentially does propose to do is that I cannot do it for arbitrary f directly, but what I can do is that I can split my f, the function, into an even part and odd part on this -1 to 1 interval. Why do I care about -1 to 1? The reason is because my operator A itself is bounded, norm is bounded by 1. So therefore, all the singular values, all the eigenvalues come from -1 to 1. But once I have the even and odd part, what I'm going to do is that I'm do a function approximation. I approximate the even part with an even polynomial, degree d, where the degree is even, and approximate the odd part of my f with a polynomial with order degree d. Okay. Now, once I have these two functions, and then what I can do is I can implement each of these polynomials, one even, one odd, with the right degree, using a quantum circuit like that. Where this quantum circuit is mostly going to use this UA, which is the block encoding of A, but at the same time, it's going to introduce some kind of like very careful rotations denoted by phi 0, phi 1, all the way to phi d, where the CR stand for controlled rotation. Okay. So now the job is that in order to implement these polynomials, apply to A, what we need to do is that we need to find out what are these angles, phi 0 all the way to phi d. Now, in quantum signal processing, so this is the quantum problem. But if you trying to find out these angles, in fact, it can be reduced to a very simple harmonic analysis problem or approximation theory problem on the matrices of SU2 matrices, group of SU2 matrices. So let me reformulate the problem a little bit. Give me a polynomial AX, which is of degree D, and it's the parity is equal to D mod 2, meaning that if it's an even polynomial, its degrees even polynomial. If an odd polynomial, the degree is odd. And also that it's bounded by 1 on this interval. What we want to do is I want to find this phase, phi 0 all the way to phi d, such that AX itself can be represented by the top left corner, the real part of the top left corner of this big matrix capital U here. So let me explain for 1 second. So what is this capital matrix U? It's essentially given by this formula at the end. It's a product of a bunch of 2 by 2 matrices where X and Z are Pauli matrices, standard Pauli matrices in the physics notation. So when you multiply them together, and what you will get, you get a 2 by 2 matrix where P are actually a polynomial, where P and Z are almost polynomials. The polynomials potentially multiply a term look like square root of 1 over x squared, 1 minus x squared, take the square root. So, and what I want is that I want this AX itself is actually going to be AX itself is the real part of the top left corner of this matrix. Okay, so now, so the way to proceed, in the literature, the following is that give me AX. What I'm going to first do is to find out what is a P is, what R is. And once I find the polynomial P and R, I can roll back to figure out what are the phase factors, phi 0 to phi d. And in fact, here I'm going to adopt the notation that I'm going to denote by PX matrix by A plus IC. So A is the real part, C is its imaginary part. And also the Rx matrix I denote by B plus ID, where B is real part, ID is imaginary part. Now, so the problem is just to, well, at least, yeah. Okay, the problem is to figure out what are the phase factor phi 0 to phi d from this polynomial ax. Now, in fact, to make things simple, what we can do is we can actually lift it into, from the -1 to 1 unit interval, this interval to a new space where t is from minus pi to pi. So in fact, this unit interval from -1 to 1, you unzip it, become the circle, and the t is parameterized from minus pi to pi. Now, so the lift process essentially is saying that if you give me a function which is fx, I'm going to be able to define a function called ft such that x is associated with cosine t, and extend it analytically. So folks, let me just give you an examples. The formula itself is probably a little bit tedious, but hard to understand, but this is easy. So that if fx is x, then ft function is just cosine t. If fx is square root of 1 minus x squared, and this ft is just sine t. Okay. Now, in terms of this, in terms of the t, this problem, that big matrix U that we had in the previous slide, can be reformulated this way: is that give me a polynomial at, I'll want to find this pt, which is the top left corner of is the real part of this pt, whether this whole matrix is represented by this. Okay. Here now you don't have the arc cosine comes up, so everything is nice. It's just t. Now, in fact, sometimes it's also useful to lift from the t space to the whole complex plane. So t is on the unit circle, right? But I can lift and do embed on a complex plane. And these functions ft themselves now becomes Laurent polynomials. So let me just give you an example. So suppose the same example, ft is equal to cosine t here. Now it's going to lift into this Laurent polynomial, which is a half of z plus 1 over z. And if ft is a sine t, then it's going to lift to z minus 1 over z divided by 2 pi. Okay, so essentially you see that all the polynomial that we try to work on the x variable now becomes Laurent polynomial in the z variable in the complex plane. Now, there are essentially two ways to try to find these phase factors. One way is to the so-called factorization approach. So this is the approach which proposed earlier. So I have 3 key papers, and the formulation we're going to use is following this Hart paper from 2019. So in the Hart paper, what you essentially do is that given a, what you want to do is that you want to find a function b such that a squared plus b squared is less than 1. Then you're going to form this 1 minus a squared minus b squared. So on the unit circle, it's actually everywhere is positive. But if you take a look at the whole complex plane, this is the Laurent series. And in fact, Laurent polynomial, in fact, it has about 2D roots inside this unit disk. Okay, this function have 2D, so it has 2D roots inside unit disk. Now what you do is that you define this EZ function is the characteristic polynomial of all these roots, multiply z to the power minus d, just to balance the degree. And then you calculate this alpha, which is a constant factor. And then finally, what you do is that you do a linear combination of EZ and E1 over Z, and that will give you a polynomial CZ and DZ, and this is CZ, Laurent series CZ and DZ. Now, once you get A and B, and you get C and D, you can recombine to get a P and Q. And from P and Q, from P and R. From P and R to calculate the phase factor is actually pretty, it's non-trivial algebra, but it's fairly easy to implement it on computer. Okay, it's just like the well-defined standard routine. Involved Fourier transforms. Okay, if you're interested, I can say more about this, but it's not directly related to how the Prony method is going to come in. Now, this is a very nice approach, and the advantage of this is direct, but the disadvantage is that you require root finding, right? You need to find these Cassi-J's in order to form this polynomial EZ. And but the root finding in high degree is in fact often not stable, because here the degree capital the lowercase d for the degree of a polynomial can in fact go to, like, say, thousands of even tens of thousands degree. So therefore root finding can be non-stable. And in fact, what you need is that you need to use extended arithmetic, and the number of bits that you need to use, it grows like a d log d over epsilon. So you need many bits to calculate these roots accurately. Now, because of this, there's also a second approach which are proposing in the literature from this paper by Dong et al. So what they try to do is that forget about all these polynomial P, Q, R, B, C, D. I just put on the head of optimization. What you do is that you just directly go find the angles phi, such that the real part of the top left corner of this U matrix, right, what I have here, so which is P, you take the real part minus A, you minimize it to make sure it's as small as possible. The downside of this approach is that it's highly non-convex. But in this paper, what they show is that if you optimize over fixed type of faces, meaning that symmetric faces, meaning that if you take the vector of the faces, you flip it, and you will get the same back. Okay, the symmetric face, and you start from a good initial guess, very special initial guess. Empirically, it leads to very good solutions. And in fact, it only uses a double precision arithmetic, so you don't need to extend the arithmetic. Now, in practice, this works quite well, but you need to restrict yourself to a certain type of phase factor and certain initial guess. And in a more recent paper, what they show is that, in fact, you can prove that this optimization algorithm can made to converge under the condition that your function A itself is not too large, it's bounded by 1 over D. Now, in practice, it seems that you don't need this, but in theory, this is necessary convergence. And this is not a problem if D is small, but if D is large, like 1,000 or 10,000, this means that A magnitude has to be very small, and this will affect the efficiency of the quantum circuit. So now here, I finally will be able to explain what is the connection with the Pronys method. Here, what we're going to do is that we're going to propose a new factorization algorithms. So we're going to follow this factorization approach to a certain extent. And then we're going to follow this new factorization algorithm, but without root finding. So we will circumvent the instability problem, the root finding. So recall that in the factorization algorithm, what you do need to do is that you need to look at this function 1 minus a squared minus b squared, and you need to find the 2D roots inside the unit circle. And this step is a key step, and then you form the polynomial EZ, right? The characteristic polynomial. And so this is the step where you have instability comes in because you need to find the roots. But the main observation is that I only need the characteristic polynomial EZ. I don't need the roots. So that if somehow I can go directly find the characteristic polynomial EZ, right? There's no need for me to find the roots, and then maybe I can circumvent the stability problem. In fact, it is the case. This is what I'm going to show you. And so what we do is that instead of looking at this polynomial, the Laurent polynomial 1 minus a squared minus b squared, what we do is that we look at 1 over this, the reciprocal of this. So the beauty of this, and the reciprocal, because it's a Laurent polynomial, so therefore the reciprocal itself can be represented by a sum of bunch of poles. Okay? Now, you recall that what are the roots of, the G is the reciprocal of 1 minus a squared b squared. So therefore the roots of this 1 minus a squared b squared, what we need to find is in fact corresponding to the poles of G, right? Because it's a reciprocal relationship. So therefore, all we need to do is figure out what are the poles of GZ, and in fact, we don't need them. We only need the characteristic polynomial of these poles. So this is where the Pronys method comes in. We take our old friend, which is this integral of GZ now over the unit circle. By doing some calculation, you see that, hey, the Fourier transform of GZ for the negative part of the negative Fourier coefficients is in fact associated with equal to the sum over all the poles inside the unit circle, and it's a negative moments of all these poles. In fact, it's positive moments because the k itself is negative. So therefore, again, we're going to form this vector, negative part of the Fourier coefficients, g minus 1, g minus 2, and so on and so forth. And through the calculation I have the previous slide, this is in fact equal to the linear combination of the moments of the poles. Now we repeat the same process. I introduce these shift vectors, and I introduce this characteristic polynomial. I know the characteristic polynomial is corresponding to a null space of this Hankel matrix. Now, previously, when I talk about analytic continuation, I do need to find the poles. But here, recall, what I need is what? I only need the characteristic polynomial. And then I multiply with z to the minus d. So therefore, I only need this. And so in fact, this is where I can avoid the stability problem. I'm just going to stop here. I don't need the poles. Once you need m, I'll be able to find the characteristic polynomial, and I multiply by z to the power minus d, and I get ez. So I get e. Okay. Now, this is not the end of the story, because I still need to be able to, I don't need to find the poles, but I still want to be able to find the m's in a stable way. So in fact, in order to find m stably, what we need to choose is that we need to choose a certain polynomial, a certain function, which we choose to be sine dt plus some small terms. Now, in the literature, in fact, sometimes people choose bz equal to 0. And what here I showed you is that choose bz equal to 0 is going to be a bad idea to our algorithms. So here in the first row, I show you the picture of what happened to bz, and this picture corresponding to this Hankel matrix here. Okay. In fact, you see that numerically, the singular value dropped dramatically. So which means that it has a huge null space. So which means that even though theoretically there's only one null space is dimension 1, but numerically it's actually very large. So this will make it very difficult to pin down what is m vector. But on the other hand, if you choose bt to be equal to the sine times sine dt, and you see that introduced in the second row of these pictures, introduce a huge antidiagonal along the matrix, along the antidiagonal of the matrix. So in fact, the zero everywhere away from the diagonal is close to zero. Along this antidiagonal, it's have a big value. So therefore, this matrix itself is very well conditioned. And if you plot the singular values, you see that it has a big singular values. Everything is between 300 to 900, except the last one, singular value is equal to 0. Okay, so this allows you to pin down the this B, the null space B vector very efficiently, very accurately. So let me show you a few numerical examples. So the first example is called Homotony simulation, where this tau here corresponds to how long you want to simulate the Hamiltonian. And this has a real part, cosine tau x, and also imaginary part, sine tau x. Now, these are the two functions that the blue and the red are the two functions that we're trying to approximate in the quantum signal processing. So, and the lapse of the time period go from 1,000 all the way to 5,000. So tau is equal to 1,000 to 5,000. And here you see how the degrees scale with these, with the tau. And this shows you the running time, how to scale with tau, and also the error. You see the running time is roughly about 2 minutes, 3 minutes, to find even the largest tau value, which is about 5,000 coefficients, phase factors, and the error is roughly bounded around 10 to minus 12. And the second example is so-called eigenstate filtering, where we're trying to pin down, we only try to project, we're trying to send the matrix A to its projection onto the singular eigenspace, which is close to the 0. So this AX is the function that we're trying to approximate, and the delta corresponds to how wide you want the window near the 0 eigenvalue to be. The small delta corresponds to difficult case, so we go all the way to delta equal to 0.005. So 1 over delta is roughly about 200s. So you see that in this case, the error is also nicely bounded by 10 to minus 12. So this is the case of the matrix inversion, where the function we're trying to approximate is the smoothed version of the inverse function. Obviously, the inverse function goes to infinity when you go to the origin, but in this case, it's near the origin. We smooth it out to make it into a smooth as a wiggle. And in this case, the kappa corresponding to the condition number, in the sense that what is the condition number of the matrix that you want to perform the inverse. So this kappa corresponds to the small kappa, kappa equal to 50 means that I want to invert the matrix with a spectrum going from 0.02 to 1. Okay, so with the big kappa corresponding to the wiggle in the middle to be narrow, so it's more and more difficult. So the degree can go all the way to about 2,000, 3,000, and it takes about a little bit more than about a minute. Well, this is 200 seconds, so it's actually 20 seconds. So this case is very fast, and also the error is bounded by 10 to minus 12. And finally, I have this Fermat-Dirac case. It's an order function. It's a step function. It's going to project the matrix into the spectrum part, which is less than 0. And you see that the error is also bounded by 10 to minus 12. All right, so this summarizes my talk, and I talk about Prony's method and talk about the two applications. And these are the papers I posted recently on our archive. So if you have you're interested, please take a look. And thank you very much for inviting me. Thank you.
Thank you. Thank you so much for the wonderful talk, Lexing.
Yeah. Okay, thank you for staying. Yeah, I don't know what happened to the network, but thank you for everyone to stay until the last minute.
Yeah, that's awesome. And we have recorded your talk, so the folks who unfortunately left the talk early, they can watch the YouTube video again, and probably they can send the question to you again. Well, I do have a question. It sounds like the Pronys method, that S operator that you try to find, that's very similar to Kuhlmann operator or the DMD, dynamic mode decomposition formalism. I'm not sure you're familiar with those methods, where you have the discrete vector. Each snapshot is each snapshot's the dynamically the stored, and then you try to find the linear operator A, which maps from previous time step solutions to the next time step solutions, and they use they apply the compression technique SVD and then on the reduced space, they do the eigenvalue decomposition to find out the dynamics in the reduced space. So that sort of formalism, it seems very similar to the Pronys method. Maybe there's a connection, and
yeah, maybe it's similar. Yeah.
Yeah.
Well, I mean, if pruning method is developed, I think it was, I don't know, it's 1791 or 1796
Exactly.
by Prony. So it's a long history, and I think it's like propagating to different communities, and people use different languages. So it's very likely that it's possible that what you described also a version of the Prony's method.
Yeah, exactly. So I actually quickly searched the internet, and I found this the paper. It's the title of the paper is a Prony approximation of Kuhlmann mode decomposition. So maybe you will be interested in.
Yeah, sure. Yeah, I'll be happy to take a look.
All right, sounds good. I will definitely go back to the recorded talk and then go into more deep.
Okay, thank you. Yeah.
All right, thank you so much,
Okay,
Lexing,
thanks a lot.
for the wonderful talk.
Thank you.
Oh, okay. Let me